Welcome. This particular lecture is going to focus a little bit more on blood pressure, particularly about how we kind of control our blood pressure and keep it at our kind of homeostatic, quote-unquote, normal 120/80 blood pressure. So in a previous slide, we determined that blood pressure is equal to cardiac output times resistance. And so cardiac output is equal to stroke volume times our heart rate. So anything that changes the stroke volume or the heart rate changes our cardiac output, which thus changes our blood pressure. Anything that changes our resistance thus changes our blood pressure. And then we can also talk about just how much volume of blood do we have. If we lose a lot of volume of blood, maybe through a hemorrhage or because we're urinating a lot, then that is going to also change our blood pressure. And your body likes to maintain very, very normal blood pressures. So we can look at kind of neural controls for regulating blood pressure. We can look at hormonal controls for regulating blood pressure. But both of those things tend to only function in the short term by either changing the resistance or changing the cardiac output. If we want more long-term control of blood pressure, it's really all about regulating the volume of blood inside our blood vessels, and that involves the kidneys and the renal system. So maintaining a normal blood pressure is not a process that is just a single system. It involves the heart, it involves the blood vessels, it involves the kidneys, it involves the endocrine system, all of which is then kind of supervised by the brain. So we're going to look at the neural controls first, and the neural controls work on what we call a baroreceptor reflex arc. When we talk about baroreceptor, we're talking about a barometer. We're talking about changing a sensor, basically, that senses when the pressure changes. So in this particular instance, it is a negative feedback. So here our stimulus was an increase in our blood pressure. Well, in our carotid arteries, in the aortic arch, we have these baroreceptors. They're basically little sensors, little monitors that detect when the blood pressure has changed in the blood flow as it moves past them. So in this instance, since the baroreceptor detected that the blood pressure went up, it sends that signal of, oh, hey, blood pressure is higher than it should be, to the brain and to the brain stem. So it stimulates the cardioinhibitory center. It inhibits the cardioacceleratory center, and it inhibits the vasomotor center. So we have less sympathetic impulses traveling to the heart, more parasympathetic impulses traveling to the heart, which causes heart rate and contractility to go down, which decreases cardiac output. By inhibiting the vasomotor center in the brainstem, we get less sympathetic impulses going to our blood vessels, which makes the blood vessels vasodilate, meaning they get bigger. That decreases resistance. That decrease in cardiac output and the decrease in resistance brings our blood pressure back into its homeostatic normal value and normal range. We can see the same thing occurs when we have a decrease in blood pressure. Again, the baroreceptors in the carotids and the aortic arch sense that the blood pressure has gotten low, sends that signal to the brainstem. Now we're going to stimulate the cardioacceleratory center and the vasomotor center, the sympathetic parts, and inhibit the cardioinhibitory center, the parasympathetic parts. The heart rate gets more sympathetic impulses, speeds up, contracts harder. The vasomotor center stimulates the blood vessels to vasoconstrict, so resistance goes up. The increase in heart rate and contractility increases cardiac output. An increase in cardiac output and an increase in resistance gets us back to our homeostatic normal range, and blood pressure has become normal again. So this is a neural mechanism involving these little reflex arcs and the autonomic nervous system. We can also look at some reflex arcs involving the neural system that are kind of triggered by changes in pressure, but are triggered by either an increase in carbon dioxide or a drop in pH or oxygen levels. Typically, those are indications that we've got a really active body. And so we have chemoreceptors in the arch and in those big carotids in the neck that also detect, oh, hey, this stuff has changed, and they will increase your blood pressure by kind of activating that cardioacceleratory sympathetic part of your brainstem to increase cardio output and to vasoconstrict the blood vessels, which will increase resistance, which increases blood pressure. If we look at kind of hormonal controls, we have several different hormones that actually result in an increase in blood pressure. Epinephrine and norepinephrine from the adrenal gland. They increase the cardiac output and vasoconstriction by stimulating the sympathetic nervous system. Angiotensin II, which we're going to talk more about in just a second, also stimulates vasoconstriction, and antidiuretic hormone at particularly high levels will also cause vasoconstriction, all of which then leads to an increase in blood pressure. The one hormone that causes lowered blood pressure, atrial natriuretic peptide, is an antagonist to aldosterone, and so it decreases your blood volume, and when your blood volume decreases, that then decreases your blood pressure. The problem with either the hormonal controls or particularly the neural controls, the receptor reflex arcs. If you have chronically high or low blood pressure, if it's kind of out of whack a lot, those receptor reflex arcs tend to just adapt and be like, well, this is what it is, this is my new normal, and they just kind of ignore it. And so they become somewhat ineffective. And so for long-term control of blood pressure, we really have to alter and change our blood volume. And our body does that by changing how much we urinate. How much blood does the kidneys filter? How much is then lost as urine. So there are two ways to activate the kidneys to regulate blood pressure. One of them is what we call the direct renal mechanism. It's all contained in the kidneys themselves. And then there's an indirect mechanism, which we've actually discussed before. It's that renin, angiotensin, aldosterone mechanism. So if we look at the direct renal mechanism first, literally it's all contained in the kidneys, doesn't need any input from hormones, doesn't need any input from nerves. Essentially what happens is the kidneys themselves sense that blood pressure has gotten, they have little baroreceptors in them as well. They sense that blood pressure or blood volume have gotten too high, and so they filter more blood, you urinate more, and that brings your blood pressure back down. The kidneys can also sense if blood pressure gets too low or if blood volume gets too low, and in that case, they'll filter less blood, they'll conserve water. That increases your blood volume, which then increases your blood pressure. So that's the kind of direct mechanism, kidneys only, completely self-contained within the kidneys. This indirect mechanism involves not just the kidneys, but the liver, the lungs, the adrenal glands, and a whole bunch of hormones. So your kidneys produce this hormone called renin when they sense that blood pressure has gotten too low. Well, renin takes this hormone called angiotensinogen, which is made from the liver, and turns it into angiotensin 1. Angiotensin 1 is converted into angiotensin 2 by a very specific enzyme called angiotensin converting enzyme, ACE. It's from the lungs. That's what actually makes this particular enzyme. Well, angiotensin 2 increases blood volume by stimulating the adrenal glands to make aldosterone, which then go back to the kidneys and tell the kidneys to hold on to more water. It also causes ADH release, and it also basically says, hey, you're thirsty, go get something to drink, and when you get something to drink, that increases your blood volume. Angiotensin 2 also then directly causes vasoconstriction, which very short term, very quickly, increases our blood pressure. So let's take a look. Here's that direct renal mechanism. Literally, the kidneys sense that pressure has gotten down. We decrease the amount of filtration going on by the kidneys. We decrease the amount of urine being formed and being excreted. That increases our blood volume, which brings our mean arterial pressure back to normal. If we activate that indirect mechanism, when the kidneys sense that the arterial pressure has decreased, that kind of stops the baroreceptors, so they stimulate the sympathetic nervous system. That stimulates the kidneys to make this hormone renin. Angiotensinogen gets converted into angiotensin 1. Renin does that. And then angiotensin 1 gets converted into angiotensin 2 by this ACE enzyme. Angiotensin 2, direct vasoconstriction, increases mean arterial pressure, increased thirst, increases our water, increases our blood volume, increases our blood pressure. ADH release, increases our water reabsorption, increases our blood volume, increases our mean arterial pressure. Adrenal cortex secretes aldosterone, increases sodium reabsorption and thus water reabsorption by the kidneys, which increases our blood volume and thus then increases our blood pressure. So we're looking at multiple systems all contributing to the control and regulation of our blood pressure. Part of the reason maintaining blood pressure is so important is that we have to make sure that blood pressure is high enough that all of the tissues are getting an adequate amount of blood, what we call perfusion. But we also want to make sure that blood pressure is not so high that we're basically busting out through our blood vessels and damaging them that way. And so we really do need to keep our blood pressure in a relatively kind of homeostatic range. A really good example is with your brain. So if the blood pressure to your brain is too low, then your brain is not going to receive enough blood, thus not going to receive enough oxygen and nutrients, and the person experiencing that will likely lose consciousness as the brain basically shuts down. However, if the blood pressure going up to the brain is too high, we could burst out a blood vessel, and now the person is having a stroke and bleeding internally in their brain, which of course is not a happy situation. So it's really quite vital that blood pressure remains in these kinds of normal ranges. Now, again, quote unquote normal is 120/80, but people's blood pressures are all slightly different. Mine is usually like 115/90, which is perfectly normal. My mom's is actually even lower most of the time. People who have really good cardiovascular health sometimes have pretty low blood pressure. As long as we've got sufficient blood pressure to make sure we're getting enough blood out to all our organs, and that we don't have blood pressure too high, that we're damaging our blood vessels and our organs, then even if it's not quote unquote quite normal, if it works for you, then we're good. This is a really good summary figure in terms of regulating our blood pressure. It looks at all of the ways that resistance can be affected, whether that's the length of the blood vessel, the viscosity, or that through that vasoconstriction, again, maybe through some sort of hormonal thing. It also looks at activating and changing cardiac output, either by changing stroke volume or heart rate. If we increase our exercise, right? If we're doing lots of exercise, that increases the activity of those muscular pumps and those respiratory pumps, which increases venous return, which increases stroke volume. If we get a less of a release of that atrial natriuretic peptide, we get more water conservation, that increases blood volume, which tends to increase venous return, which tends to increase stroke volume, which increases cardiac output, which increases mean arterial pressure. Whether we've got some sort of fluid loss, maybe because we're sweating like a crazy person because it's 105 degrees here in Georgia, that decreases blood volume and decreases blood pressure, and so the kidneys will conserve more water. When we conserve more water, we increase the blood volume, increase venous return, increase stroke volume, increase cardiac output. So it's a really good kind of summary figure in terms of blood pressure regulation. I definitely recommend checking it out.